Hello everyone, my name is Victor and welcome back to Senior Mathematics. We'll spend the last two videos focusing on differentiation, like finding slopes and optimizing functions and whatever not. Now we'll go to the other side of calculus. We're going to go into integration. And now we're going to see how differentiation and integration are connected by the most important theorem in all of mathematics. So we have this theorem right here, right? This is the question that pops up and really started the whole integration thing, which is how can we calculate this blue area right here? Like can we calculate that? And asking what's the area of this shaded region between the curve and the x-axis from A to B. Now, this shape right here is not a rectangle or a triangle because this shape really curves, and so we kind of need a new tool to calculate this. And so, what I want you to see is integration is the reverse of differentiation. What we did with differentiation was we did some form of this, where if fx was x squared and we want to derive this, and we will have something like 2x. Now we're going to go antiderivative. So we'll go backwards actually. So we'll go, let's say, if we even have something like fx is fx here, which means x here, then we'll have to go something like, basically like this. So we have to go all the way in the reverse. We have to go in an antiderivative way, go backwards. So we have to go, the antiderivative of 2x is x squared. So the fundamental theorem says that the definite integral of f from a to b, here a to b, equals f of b minus f of a. This is big F, okay? And big F usually means antiderivative, where F is the antiderivative of small f. So look at big F, antiderivative, small f is usually derivative. So what we want to do is we want to find the big F, which is antiderivative. We're going to plug in the bounds, which is from A to B, and then we subtract. We're going to subtract A from B right here. So let me just clean all of this so we have something for our workspace. We're going to be solving our first example to see how it looks like in real time. Of course, we have our first example right here. From A to B, from 1 to 3, we need to find the antiderivative of x squared dx. Now let's just write that out right here for everyone to see. I'm going to zoom out, not too much. Going to put it over here. I will write the antiderivative form. So the general rule. So I want to write antiderivative now I want of x to the power of n. This is the general rule, of course. This will be x to the power of n plus 1 divided by n plus 1. This is the general rule. Increase the power by 1, divide by the new power. This is the power rule in reverse. So what we need to do is to solve this first example. We need to write the antiderivative. So this is step number 1. Write the antiderivative. So we have the big F here, fx. This is the general rule. I will write for you the small f and the big F first to let you know what we're doing. So the small f, what is the small f? Our small f is x squared. What we need to do is to change this into big F. Now big F requires us to go through a process of make this antiderivative. So we need to make it, so this is 2. So I plug this, if this is 2, then n plus 1 would be x to the power of 3, and n plus 1, 2 plus 1 here would be 3. So we have found our big F, the antiderivative of x squared, which is small f, is x cubed over 3. Now, because I have found the antiderivative, I need to calculate and evaluate at the bounds. So I have the bounds from 1 to 3. If you look at the rule, from A to B means FB, big FB, minus big FA. So I'll go big F3 minus big F1, big F3 minus big F1. What I'll have is that I'll have 3 to the power of 3, or 3 cubed over 3 minus 1 cubed over 3. And this would give me more space to write, of course. 27 over 3 minus 1 over 3. This would give me around 2, 8 and a 2.5 square units or so. So f of 3 is 9, because this is 27 divided by 3. This is going to be 9. F of 1 is 1/3. 9 minus 1/3 is 26 thirds. So I'm putting this as 8 and 2/3 square units. So to solve this, the area under this curve here is 8 and 2/3 square units. If A is like 1 and B is 3, the values can change. Okay? And when we do that, we want to check by substituting back. This is a very good habit to have, and it's like a channel classic at this point. So we need to check. So we check. So we need to check the derivative of the big F form right here. So we need to check it. We need to somehow check. So we're gonna throw the 3 over here. So we have 3 multiplied by x 3. I have the minus 1 here. This is the classic power rule. Those are 3 here. 3 divided by 3 multiplied by x squared here, because it's 2 now, divided by 3. I'm going to eliminate the 3's. We have x squared. So we want to check by substituting them back. Differentiate this. Differentiate the x cubed over 3, and you will get x squared. So the antiderivative is correct, and so the integral is correct. Remember to do the checks in your own notes to make sure that you don't have any, you didn't do anything wrong or something like that. Yeah. So let's get into our next example. Get to example number 2. Let's do something that is a little bit more difficult, a slightly harder one. We're going to find the integral of 3x squared plus 4x from 0 to 2. Now we need to write that up, of course. So let's write this up. We need to write to 0 to 2. So this would be 0 to 2 right here. And so 3x squared plus 4x, of course, and dx. Whenever you see this form, we're asking for the big F form. When you see dx form, you're asking for that form. So we need to write the antiderivative term by term. So we need to change 3x. We're looking for antiderivative here. So we need to look back at our general rule here. We will plus 1 into the power, and we will divide by the new power. So we'll write it here, 3x squared plus 1, and divide that by 2 plus 1. This would give us 3 multiplied by x to the x cubed, and this would divide by 3, and this would give us x cubed. So x cubed. The next term is 4x, so we need to antiderivative it. So we need to put it because this is to the power of 1. If it doesn't show any kind of power, this is to the power of 1, so we need to check it. 4x 1 plus 1, just plus 1 into the power when you're doing antiderivatives, and then you bring this power down here as well, so 1 plus 1 here. This will be 4x squared to the 2 here, divided by 2, so this will be 2x squared. So we have found the antiderivatives of both terms. So time to write, this is small f, by the way. Small f is 3x squared plus 4x. This is small f. We need to find big F now. So big F will be written in this form of x to the power of 3 plus 2x squared. Okay, so we have found the antiderivative forms. Now, what we need to do is we need to find the values and how it subtracts at the bounds, of course. So we're gonna rewrite this for you to easily see. I'm just rewriting this. Now I need to substitute the values together. Remember, we have the bounds from 0 to 2. So let's find out where the values of f0 and f2 are currently at. I'll calculate this pretty quickly. So this is f0 will be 0 plus 0 because both factors are 0. And f2 here means 8 plus 8 as well. It's pretty standard. This will be 16. So if we were to calculate, we have found the values of the bounds. We need to calculate the subtraction of this antiderivative form right here. To the evaluation of that would be equal to big F2 minus big F at 0. This would give us 16 minus 0. Of course, this would be 16 square units. So f of 2 is 16, f of 0 will be 16, and the integral will be 16 square units. Now, of course, we just did our very good habit of integration is the reverse of differentiation. But we also need to check by substituting them back. So let's do our check right here. So we need to check the derivative form of the n of the big F that we just created. So we need to put them like this. We need to check 2x squared. So we need to derive this. So we do our classic shortcut here. So 3, we'll throw 3. So hold up. So let me just write it like this for it to be too easier if you're not too used to this. X to the power of 3. We will throw the current power next to x. 3 will minus 1. And this will give us 3 squared, x squared. Continue for the next one. 2, next term. We want to throw the current power, next to here. So 2 multiplied by 2 multiplied by x. 2, just subtract that by 1. We will have 4 multiplied by x to the power of 1, and it will be 4x. So this will give us the form here of 3x squared plus 4x. And our differentiation will be matching the integrand. You have to check where our differentiation will be matching our original form right here, the small f. Yep, and it actually fits. So that is correct. That is confirmed. And so we'll be closing here with looking into the original form here. That's very important, where you have to know where the differentiation and integration are inverse operations. They undo each other, basically. The differentiation will give you the slope, while the integration will give you the area right here. And this cycle, basically, is like the core of all calculus. And so what I want you to remember, of course, integration is the reverse of differentiation with this habit. You want to find the big F from the small f. Okay, finding the antiderivative plug in the values from the bounds from 1 to 3 here. Make sure to let the bigger value subtract the smaller value. Always check by differentiating. What I mean is that making sure your big F form goes from small f form. Okay, find your small f, find your big f's, and let it go from big F back to small f. See if it match, and then when it matches, you have gotten yourself a very good check. You have secured your points, and yeah, you just get your max score from these problems. So in the next video, we're going to leave calculus for a little bit, and I'm going to be moving next to mathematical proof, which is called induction. I'll see you there. Thanks for watching.